Second lecture on topological machine learning. Today is all about graphs and graph learning, and the first half of this lecture is structured to give you an overview, a crash course of graph learning. And so I might repeat a couple of things that you've already seen in other courses. If that is the case, then I'm very sorry about this, but I'm trying to put us all on equal footing. And the second half of the course will then be about topology-based applications in graph learning. So various things that one might want to do here. We'll have to see how it goes with the break, because it might be that this part is a little bit shorter and then we might have an earlier break. I don't know how flexible we are there, but if not, we can certainly also spill over a little bit and see and discuss the second aspect of the course as well. All right, so I'm going to start from the very basics again, but don't worry, we are not going to investigate and invent persistent homology again in this course. So I just want to put us, as I said, all on equal footing. So a graph in this lecture will just be a tuple of vertices and edges denoted by v and e respectively, and the edges are typically just subsets of paired vertices, which also gives you an understanding of the fact that I typically ignore the directionality completely. Adding the directions and taking directed edges into account is a whole other thing. It might be worthwhile if you're interested in this. It might be useful to discuss this later on, but right now, I would say, well, we stick with the undirected one. Of course, if E then is ordered, then you would call this graph directed, and this is a classical example of a graph. It's one that I pulled from one of the classical benchmark data sets. It's supposed to represent a molecule, and I kind of like it because to me it looks a little bit like a fish. I do want to stress, though, however, before we move on, I do want to stress that in a very real philosophical sense, what I'm showing you here is not the graph, right? It's a visualization of the graph. So if you are a hardcore graph theorist, and we will see an example of this in a couple of slides, then this graph doesn't exist in terms of a visualization, but it rather just exists as an abstract object. And the reason why I'm mentioning this is not to have a deep philosophical debate about what it means for something to be a graph, but rather to tell you that we often assume that we have some underlying geometry of the graph, but this is not always the case. And to see what I mean by this, let's take a look at some alternative views on graphs. So what could graphs be? So certain people think that a graph could be, for instance, a triangulation of a manifold. So it arises as you take a manifold, you triangulate it, and then you take the vertices and edges arising from that. Another thing could be to say that a graph is rather something like a one-dimensional simplicial complex, which already gives you an understanding of the generality of that notion, because you could say, well, if there are simplicial complexes, then I take some time to think about a specific type of simplicial complex, and I call that a graph. Of course, you could also say, well, a graph is some kind of metric space. Of course, there's not necessarily a direct correspondence, right? So not every metric space is a graph, of course, but you can, of course, realize a graph as a metric space by using something like a shortest path metric, for instance, right? Now, the final and most comprehensive definition, I would say, is to say that a graph is nothing but a set system. So all these views are valid, but all these views are also including and excluding certain criteria and certain aspects of a graph. Now, having said that, what is graph learning typically? Well, graph learning refers to taking one of these graphs, whatever your view of the utility or of the provenance of the graph is, and then perform a variety of tasks on them. There are three different types of tasks that you will often encounter in the wild. There's also different tasks that you could do, but these are I would say, most common ones. The first two ones involve classification and regression, respectively. So classification meaning that you take a full graph, you tell me that it has a certain label, it might be a poisonous molecule or whatever, or you take a node and you classify that. So the node might represent a person. You could classify this person as being part of a certain friendship group, or you could classify an edge and you could say, okay, this is an edge of something like these people are friends or these people are enemies or whatever. The same goes for regression. In regression, you predict typically something like a continuous attribute or even an attribute vector. So you could predict the solubility of a molecule. That would be a graph level task. You could predict the maybe income of a certain person based on its friends. That would be a node task. Or you could predict the amount of times people meet each other based on the existence of an edge. The final task involves just predicting the existence or the non-existence, the absence of edges, and that is often known as link prediction. All of those have their utility, all of those have their different applications. I will mostly be talking about classification here, and also mostly talk about graph level classification, because that's I can say that this is maybe a more the most comprehensive and the most common task that one can easily illustrate and understand. Now this is somewhat whimsical, but I want to mention it because I think it's important to also discuss this type of meta information that we often ignore when we do machine learning or any type of data analysis. So there's a collection of, let's say, different attitudes about where do graphs actually come from. And I'm following some scheme that you might recognize from some games in the internet. It's a game called Dungeons and Dragons, where you have alignments that tell you whether something is lawful, neutral, or well, let's see about that, right? So a lawful alignment would be that would incur the belief that graphs only occur in graph theory. So because graph theory is the field that deals with graphs, so this is the only field that the graphs occur in, right? A neutral alignment would be that graphs can arise from other data modalities, and we'll see some examples of this in a minute or so. And the chaotic alignment or chaotic belief could be that everything is in some sense a graph and we just don't understand it. And I'm not mentioning this just for the fun of it, but I really believe that there are underlying attitudes in the community that we don't often talk about and that we don't often analyze in our data sets later on. Because depending on the alignment that you have, this might change your view on data, and this might also change what type of data and what type of tasks you consider relevant. And to underline this, let me give you an example that I actually took from a website called houseofgraphs.org, which is a great collection of interesting graphs. And they state that most graph theorists will agree that among the vast number of graphs that exist, there are only a few thousand that can be considered really interesting. And this is remarkable, because if it's only a few thousand, this would mean that a lot of the graph learning tasks that we want to do can essentially be, well, mitigated and done by a very, very simple classifier, because we don't need a very deep neural network to do the classification of just a few thousand data points, right? We could solve this differently. So clearly you can see that this cannot be the whole truth, because when you look at the data sets that we have, you will find that there's a vast amount of graphs out there, a lot of molecules, a lot of point cloud-based graphs, and so on and so forth. And all of these arise from in different ways than someone from graph theory would think about. And that, I think, is the most interesting thing about graph learning at this point. It's not about dealing with graphs as such, but it's also about dealing with graphs that have some kind of geometry attached to them. Now, let me give you a couple of examples of how to actually get graphs in practice. It's quite possible and easily feasible to obtain graphs from point clouds, for instance. So you can start with a point cloud like this one on the left-hand side, and you can turn it into a graph by, for instance, calculating the so-called RIPS graph, or also known as epsilon graph, or maybe also sometimes known as neighborhood graph at a scale epsilon. So this is a very simple construction. It's also a very deep construction in the sense that you can build much more than just the graph from this, right? But fundamentally, it just boils down to, you take a graph, you take your points, your data points x, so these become the vertices, and the edges are defined based on evaluating a distance function between them. So whenever two points have a distance less than or equal to epsilon, you connect them by an edge. And this leads to this type of graph on the right hand side. It's just one construction, and notice that even though we're talking about computational topology here, I won't talk about anything like how to choose epsilon in practice or whatnot. I'm just saying that if you want to, you can go from a point cloud to a graph, and you will get a graph at a certain scale. Whether it's the right thing to do, that's something very, very different and very difficult for me to answer in practice though. Now, there's also ways to obtain graphs from time series. So you take your time series, at least if it's a univariate time series, and you can build a so-called visibility graph. The visibility graph is defined by taking a kind of literal point of view in which you try to see which points can be seen without intersecting the time series itself. So you connect observations at points I and I+1 if there are no other observations along their linear interpolation. So if they don't intersect the time series as such. That's a very interesting construction from La Casa and colleagues based on their paper From Time Series to Complex Networks, the visibility graph. It's a PNAS paper from 2008. And the visibility graph has shown some very intriguing properties in terms of understanding the dynamics of complex system and complex networks. So indeed, this is a very, well, non-canonical but useful way of turning a time series into a graph. Now, there's of course a difference between those types of graphs and other types of graphs. Namely, some of these graphs that we've seen, they arise from some prior geometry. So we start with a geometry with a point cloud, and then we turn those into a graph. That also means that all the attributes that we collect about these graphs, they reflect this geometry to a certain extent, right? And this also means that when we're studying these types of graphs, we are also actually studying their geometry, or this underlying geometry, or by proxy, we are studying something other than just the graph connectivity. And the reason I'm mentioning this, if this feels very philosophical to you, the reason I'm mentioning this is that it's really hard in graph learning to decide what constitutes a good graph to learn on and to learn from. And these type of considerations based on the provenance of graphs, based on the construction of the graphs and so on, they might shed some light on this in practice. And to emphasize and underscore this point a little bit more, I want to point out something that we did last year, although the paper just occurred now, it's finally published. And somewhat whimsically, I could say, what's in a graph, right? So this is a paper with Corinna Coupet and Yildiz Recken on hypergraph dataset constructions. We called it All the World's a Hypergraph, a data drama, and it might be well worth the read. I do want to emphasize this here on screen and on lecture that we wrote this paper without the help of large language models because it is written as kind of a theatrical play, and so we had some fun doing that. The point of doing this is that we wanted to highlight how much your modeling decisions influence the outcome of the graph construction as such. And to this end, we looked at plays by William Shakespeare, mostly because they were available in a good format. They were in the public domain, and they're sufficiently old so that we don't get into any trouble with anyone. And what we found is that it's very easy to construct different so-called co-occurrence networks. This is a classical construction that you will see a lot of times when you're dealing with complex networks or with complex systems. You will see that people are turning all kinds of things like a musical or like a book into a co-occurrence network, meaning that you want to see who is talking to whom in which chapter and so on and so forth. And there's a lot of ways of doing this. I urge you to read the paper to find out which which ways are specifically useful. But what we found is that there's multiple ways of constructing this. And if we do this, let's take a look at 3 different co-occurrent networks. All of them are valid in the sense that all of them measure some kind of co-occurrence. One could measure, for instance, just the fact that two players or two characters in a play are mentioned in the same chapter. One could look at more intricate things like stage groups or even acts and so on and so forth. But fundamentally speaking, none of these are more or less valid than the others, right? But they are very, very different in the sense that they show different types of characteristics of the play. So without delving into that, that's from Shakespeare's Romeo and Juliet. I don't want to spoil it for you, but let me just point out that it's a tragedy, unfortunately. And one thing that one of the networks might change is that there is no proper direct interaction between Romeo and the Capulets. So these are two different families. They're warring, right? And Romeo is the scion of one of the families, and the Capulets are from the other family. And they are not really interacting directly, but some of the visualizations and some of the co-occurrence networks make it seem like this is the case. So in a very real way, and I hope you understand that this transfers to a lot of other data sets that we're seeing, in a very real way, the modeling decision that we did, namely the construction of the graph as such, the construction of the graph from the data, introduces some kind of new information. In this case, it's information that might be considered wrong because those characters are actually not on stage together, but nevertheless, it's information that is in there. And if you were now to take this data without understanding how it has been constructed, and you would use that for some graph learning task, then you might be in a bad place because you might end up solving a task that is actually not worth solving. Now, this sounds very pessimistic, but I just want to point out that modeling decisions and provenance of data matters. Now, let's pick up the pace a little bit and discuss rather, suppose we have a nice graph and a good graph learning task. How do we actually represent graphs? And this is where things get interesting, because two graphs in general have, of course, a different number of vertices and a different number of edges, right? But this means that to really work with them in a machine learning setting, you need a way to vectorize them. You need a way to embed them in some kind of vector space in a way that is not dependent on the number of points or on the number of vertices, to be more specific, in the graph. Because otherwise, for every graph that you change a little bit, if the graph size changes a little bit, you end up getting a different representation. And to get a function f that maps from the space of all graphs into a nice vector space, you need to make sure that this map is permutation invariant. Permutation invariance refers to the fact that the ordering in which you provide the nodes and edges of the graph should not influence the outcome. So, and this is, when you think about it, this is a very valid and intuitive construction and property that such a map must have, because in reality, the ordering in which we number the nodes, they don't matter, right? It's a graph is about its topology, and so if you change the ordering because you specify the vertices in different order, then of course your representation shouldn't change. And in a very real way, you could say that graph learning is about finding these type of permutation invariant functions. Now, let me briefly diverge into some kind of historical considerations here. So there are essentially two big camps of approaches for how to address this. The first one is one could call shallow approaches, which doesn't mean that they are bad or that they are not well thought out, but just that they don't make use of deep learning techniques. The other one is of course your deep learning stuff that is coming in, and we'll see some examples of how that works later on. So for the shallow approaches, I'm mentioning this for the sake of consistency and for the sake of completeness. There are architectures like Node2Vec, which uses an encoder-decoder architecture and some random walks to essentially take nodes in a graph and embed them in a high-dimensional space. There's also the very venerable, and I still consider them to be very interesting, the graph kernels, which are feature maps of reproducing kernel Hilbert spaces, if you're familiar with that. And there's also, of course, embeddings based on things like the graph Laplacian or the Hodge Laplacian and things like this. On the other side, we have the more deeper approaches, which make use of the fact that you can stack neural networks like Lego bricks in a way, right? And there's a ton of different networks now around. So this little list here of 3 doesn't really do them justice. So I urge you to look into some recent surveys here. But just if I had to pick 3 particularly interesting specimens, I would pick the graph convolutional networks, the graph isomorphism networks, and the graph attention networks, specifically because they contain in a very real sense, they contain the kernel and the nuts and bolts of everything that you need to know to understand modern graph learning techniques. Now, before we delve into that, I want to take a little bit of time to talk about message passing, which is still the predominant paradigm in graph machine learning at this point. As a caveat and a disclaimer, I do want to state that there are also neural networks, or graph neural networks, I should say, that don't use message passing information, but the large variety of methods and architectures that we're seeing means that the biggest chunk of the methods is actually based on some form of message passing. And message passing is a very simple but powerful concept. It essentially goes like this. It says that suppose you have some kind of messages attached to your nodes. The messages could be something like vectors in a high-dimensional vector space, right? Then you can take these messages and you can exchange them across neighboring nodes, and you can aggregate them using some kind of function. Now, this some kind of function could be a sum or a mean or some other permutation invariant function. And that essentially gives you a process that assigns to every vertex in the graph another set of attributes based on the attributes of its neighbors. And therein lies the beauty of this technique, because the type of aggregation and the way you work and continue to process those attributes, that is where you can instill your domain knowledge, and this is where you can add different parts in an architecture. And let's take a look at how this works in practice. So you start out with for instance, node D, and you take a look at its neighbors B, C, and E, and then you take their messages and you aggregate them using some kind of function. So you aggregate over X, Y, and Z. And this can actually lead to a large variety of different graph neural network techniques based on how you continue processing this information. So this is a very nice schematic overview from Petar Velikovic and his great paper, Everything is Connected, Graph Neural Networks, which appeared, in Current Opinion in Structural Biology. And essentially what it says that the graph neural network allows you to go from some kind of inputs on the graph to some kind of latent representations in the graph, and then further on, depending on what type of task you want to solve, you can aggregate this information in a different fashion. So for instance, if you want to do node classification, you just take the latents as they are and you apply some kind of additional function to them. If you want to do graph classification, you first have to aggregate further over them, right? Because you have to take all the hidden representations in your graph to make it work. And if you want to do link prediction, you typically take the hidden representations of the source and target node of your edge to decide this in the end. And this is a very, very powerful paradigm, as you can see. In particular, you can define a lot of interesting architectures in practice by following this kind of almost, I should say, recipe. It is a recipe, right? And to see this, I borrowed this schematic from a great book by Michael Bronstein and colleagues on geometric deep learning, grids, groups, graphs, geodesics, and gauges. It's also known as the 5G book, and it's a very, very good read. So notice that to build some graph neural network architectures from the components that we've seen, we take two neural networks, phi and psi. So for instance, the psi could just be your usual ReLU network, right, with one weight matrix and some bias. You take any permutation invariant aggregation function. It always looks a little bit like a sum, of course, right? But in practice, it can be something different. And then you have various ways of building different architectures. You could have a convolutional architecture which applies phi to this to the attributes of a node and the sum or the aggregated attributes of its neighbors. You could have an attentional architecture which adds an additional attention term depending on how relevant the connection between U and V, between the source and the target is. Or you could have a very, very general architecture where you just throw psi into the mix, and you make the existence of an edge, or you make the transport process depend on both the source and the target. Whereas in the other types of architectures, you only use the source node or the neighbor if you want. Now, this is by no means comprehensive, because there's of course a bunch of other ways to set everything up, but this gives you hopefully an understanding of the relevant building blocks of graph neural networks. Now, moving on a little bit, what are we interested in once we have those, right? We can always build them and we can solve a task with them, but that doesn't necessarily tell us how good they are. It just tells us how good they are at a specific task, at a very empirical way of looking at the world. What we're really interested in when we talk about graph neural networks, or in general any graph learning algorithm, is we're interested in measuring the expressivity of the architecture. And expressivity is typically, but not always, measured in terms of graph isomorphism. So graph isomorphism is a way to, well, figure out whether two graphs are isomorphic. So you have two graphs, G and G prime, you have the vertex sets V and V prime, and then a graph isomorphism is of course a bijection between the vertex sets such that two nodes are adjacent if and only if their images are also adjacent. And there's a very simple recipe, I should say, for how to become famous, not only in machine learning, but in computer science in general. And that is, you just have to prove that the graph isomorphism problem, so the problem of deciding whether two graphs are isomorphic, can be solved in polynomial time for arbitrary graphs. Because in reality, we don't know that yet. But this is a way to measure the expressivity of a graph neural network in a model in general, namely studying its capabilities of detecting isomorphic or rather non-isomorphic graphs. And how is that typically done? Well, it's related to a very intriguing and also almost historic procedure from the 1960s, the so-called Weisfeld-Lehmann test for graph isomorphism. The Weisfeld-Lehmann test exists in many different ways, but here I'm now giving a very nice folkloristic variant. If you're interested in more of those, I will give a couple of additional resources. In particular, the work by my colleague Christopher Morris from Technical University of Aachen is very, very relevant and interesting in this regard. Now, the Weisfeld-Lehmann test works as follows. You start with your graph, and you first create a color for each node in the graph. This color can be based on the label or its degree or whatever you prefer. Now, I'm not meaning a physical color in the sense, right? But it's just very nice to think about it in terms of colors, and you will see that I use this terminology in the subsequent slides. Now, what you do in the second step is you start collecting the colors of adjacent nodes in a multiset. So you take all the colors and you count their multiplicities. Then the third step is you take the colors in your multiset and you compress them together with the original color of the node to form a new one. And this compression is where the fun happens, because this compression needs to be lossless or perfect, in the sense that whenever you have the same input of a specific node color and a specific multiset, then the output needs to be the same color. In different terms, you could say that we're looking for a so-called perfect hashing function. So it's about hashing nodes and node neighborhoods. And the nice thing is, once you have done this, you're exactly where you started, but with different colors, which means that you can continue this relabeling scheme. And the great insight by both the authors of this paper is that this relabeling scheme actually is bound to converge until after a finite number of steps. So the colors will be stable at some point and won't change anymore up to normalization. And the great insight is that if the compressed labels, so these new labels of the two graphs, if they diverge at any point, so if you have a sequence of colors for the nodes and they diverge at any point, then the graphs are guaranteed to be not isomorphic. Now, here I have a warning sign because that's really relevant to understand this in general. The other direction is unfortunately not valid, because otherwise you would have a very nice polynomial scheme, right? So there are non-isomorphic graphs that can give rise to coinciding compressed labels. So in the parlance of the WL test, as it's also sometimes called, this means that there are non-isomorphic graphs that WL cannot distinguish. And I really want to emphasize that there are failure modes of this algorithm, because they will be relevant for the second lecture. Now, let me give you an example with just one step of the algorithm, but I think it's sufficient to explain everything. So suppose we have this nice graph here. It has blue labels and red labels. And the first thing we do is we just tabulate everything. We look at a node and we look at its own label, and then we look at its adjacent labels. So for instance, take node V3 here. It is a blue node and it has 1, 2, 3 blue nodes as neighbors and 1 red node as a neighbor. And so you can see that it is represented by exactly that in the table: 1 blue and 3 blue and 1 red. Now, you do this for all the nodes and all the neighborhoods, and in the next step you hash all of them, meaning that you compress them to a new label. And as I said before, and I think I did this right because I ran this a couple of times now, the hashed label is uniquely determined by the color of the node that you put in there, so by the own label and the adjacent labels. So for instance, you will see that let's say blue and blue gets hashed into green. Don't attach too much meaning to this. This was just something that I did, right? There's like no color mixing involved here. And red and blue together will be mixed into something like this violet here. And we can now take all these hashed labels and we can relabel the graph. And if you paid some attention, so I'm going back and forth now a little bit, you will see that there's a very interesting phenomenon happening. Namely, the labeling scheme apparently gives you also a way to find out something more about the role or the relevance of a node in a graph. So you can see that all these blue, which used to be blue, all these blue leaf nodes of the graph, right? They all become the same color here. Whereas this very central node that has very diverse neighborhoods becomes its own color. So you can already guess that this procedure gives you some kind of inkling of an understanding of what is going on in that graph. And indeed, this is why it was so relevant and why it is still being used. Because a very simple procedure, if we think back about what we wanted to do earlier, the representation that is permutation invariant, a very simple procedure to get such a representation from the WL test is to take the labels and their counts and to turn them into a feature vector. So you just take all the labels that you see here, turn them into a count vector, and then you can compare the graphs based on these feature vectors. And notice that you can always do this because you just have to decide about your perfect hashing scheme and how it kind of enumerates the node labels. So that's really nice. It's relatively simple to implement, and it's very powerful. And indeed, this is a very surprising result, and this is where the papers by my colleagues come in very handy. A very surprising result is that most message passing neural networks are no more expressive than the WL test for graph isomorphism, which means that even though the WL test is a very simplistic procedure that is very static in the sense that you don't have a lot of control of what is going on, right? If you have your labeling, you just go ahead with this, right? But nevertheless, the GNNs are no more expressive than this procedure. So To learn more about this, please check out the work by my colleagues Chris Morris and colleagues on WL Go Neural, or Weisfeld-Lehmann Go Neural, higher order graph neural networks, or the great work by Xu and colleagues on how powerful are graph neural networks. So this is also why this test remains relevant to this day. Now, before we move to the second part on topology and topology-based graph learning, I do want to point out that the current graph neural networks that we have, they are not without their issues. So one thing that you will find is the so-called issue of oversmoothing, which is essentially saying that if you have too many GCN layers or too many message passing layers, too many rounds of message passing, you don't always get higher performance, but sometimes you indeed get a way to hide the signal because there's so much passing going on that essentially everything becomes an average signal. And you can see this in a very nice figure which I reproduced from Chen and colleagues on measuring and relieving the oversmoothing problem for graph neural networks from the topological view in the AAAI conference. So you first have one GCN layer. You have a very bad performance. You add a second one, it goes up to 0.8. Okay, that's great. You add a third one, well, it's still kind of okay. A fourth one, it goes a little bit down even more. You add a fifth one, and then you drop. And with the sixth one, you're back worse than you started. Now, this can be a problem in practice, in particular for graphs that have a very, very high diameter, and there's various ways and techniques to mitigate this. I won't have the time and space to go into all the details here, but I do want to point out that your regular graph neural networks are not without the issues, and this is also a motivation for the subsequent part of the lecture, which shows you why topology is relevant and interesting in this case. There's also other things that are problematic in the GCN realm. So, for instance, my colleagues Chen and co-authors have a paper on can graph neural networks count substructures. That's in Europe's paper from 2020, and they found that there are a lot of things, a lot of properties in a graph that your regular graph neural network might not be aware of, such as the number of connected components in a graph, the number of certain substructures in a graph, so for instance triangles or three stars or other types of motifs, and the number of cycles of arbitrary length in a graph. In particular, this last one will come in handy next for the next lecture, because we will be developing a new architecture that incorporates such information. And I'm mentioning this not to say that these networks are useless in practice, because on the contrary, they are really, really useful in practice. It's just that they have their caveats and they have their limitations, like any computational tool. Now, let's briefly take stock before, maybe depending on what the organizer is saying, we take a brief break and then we continue with the other part. But let's briefly take stock before we march on. So graphs are often, but not always, the right modality for your data. So I showed you a couple of ways of representing different types of modalities as graphs, but you fundamentally have to decide whether a certain representation is correct or not. The field is definitely ever growing. So there's lots of attention on the field of graph learning now. Message passing neural networks, graph neural networks are used in a lot of domains, in particular in drug discovery. But there's also a lot of new frontiers that we have to understand. There's the question of how to integrate higher order information, like the existence of certain cliques or simplices. There's also the question of how to integrate dynamics, right? What happens if you adjust your graph structure a little bit? And there's also the final frontier, as always, is the expressivity. So how good is your model in practice and what can it do? And with this, I'm at the end of the first part of the lecture, and I thank you for your attention, and maybe we can take a couple of questions already.
Thank you very much.
Thank you.
There's already a question in the chat. Maybe you can read it. Could you please point to some practical applications so we can get a concrete picture? Maybe a paper or a study?
Yes. Wait a second. I need to pull up the chat again and put this on the second screen. So there's a lot of practical applications in graph learning. one of the most famous ones I should say is probably drug discovery, where you take molecules and some kind of fingerprint information of a molecule, and you want to figure out whether this molecule has certain beneficial properties. That is a very relevant question that pharmaceutical companies are willing to pay a lot of money for solving this better than others. There's also the question, of course, of generating such structures in the first place. So not only classifying them, but also generating them, or generating them under some kind of feasibility constraints, and seeing that they can actually be synthesized in laboratory. So those would just be two big ones that come to mind. Let me see, is there another question?
Not for the moment. Yeah, a minor question. I mean, how large are the graphs that you are considering here?
That's a very good question. So they range from having a couple of dozen nodes to having a couple of thousand nodes, depending on the application. So funnily, many of the problems in biomedicine that involve proteins or molecules and these sort of graphs, they're actually not too big. So there's lots of them, right? So they are big in terms of big N, but the individual graphs are rather tiny, I should say. And this is also really interesting because it also gives you it makes it easier essentially to apply topological concepts, because we're not necessarily in topology, or okay, maybe I don't want to make any new enemies here, but in computational topology, a lot of the methods are not really that scalable to very big graphs or very big simplicial complexes, but they easily scale if you just have lots of small things, right? Because then the computational performance is not necessarily the bottleneck. So this is something that can often be exploited in graph learning.
Maybe another question. I think that maybe I'm simplifying too much, but it seems to me that there are two kinds of graphs. I mean, graphs with a few edges and graphs which are almost complete graphs. But nevertheless, they are interesting because maybe the edges are labeled, or I mean, what you have to do with them is very different, right? Depending on the sparsity of the edges.
I agree. Yeah. So indeed, I think many of the applications have either very sparse graphs, or for things like link prediction, you often work with very dense graphs. So there's not a lot of things in between. And I think actually some of my colleagues have been looking into that. There's a paper by Brian Perosi from Microsoft Research on what he calls graph world. So I think the title goes something like "Synthetic Graphs Bring Real Insights" or something like that. And this shows exactly what you said, that there's like a large, vast space in the space of graphs that is typically uncovered by data sets.
Thank you. Now there are two questions in the chat.
Oh yeah, okay.
Can you read them?
Yeah, there's one on regarding high order information. Are you aware of any case study implementations of simplicial neural networks, that is neural networks in which we also consider higher dimensional links between the neurons? Well, I'm aware of simplicial neural networks as a way to deal with simplicial complexes, but that's probably not what you had in mind. So no, I'm not aware of any neural networks that consider essentially like a higher dimensional links between the neurons. This is definitely something new, but very exciting for me. And the other would be, maybe if there's follow-ups, we can take them, right? The other would be on the WL coloring theorem. It seems that the initial coloring will determine the outcome. Is there a way to build the initial coloring setup? Yes, there is a way. That's a very good question. So typically the coloring is done based on the degree, for instance, of a node, or based on the labels that you already have, right? So in some sense, labels and colors are interchangeable, but I wanted to ensure that it's clear that this is a general procedure. So it's not tied to necessarily labeled graphs, but it can also be applied to unlabeled graphs. But indeed, you have to pick the right vocabulary for both of the graphs to be comparable. And so people typically do the degree, or if they have it available, the labels of the graph. Hope this helps. Wait a second. I think there's another one. Oh no, okay. No, it's just Zoom showing me something.
But Bastian, you wrote here, it is still in the screen, that new frontiers include higher order information. So what did you have in mind for this?
Yeah, one of the new frontiers is definitely to include information about things that go beyond just the nodes and edges. So for instance, if you have a simplicial complex as an input, can you actually transport information across the simplices? That's still something that is currently investigated. I mean, there are some architectures out there that already do this, that already promise to do message passing on simplices. But there's also always the question of, can we do something beyond message passing, or is everything that we're doing some kind of message passing between appropriately set up graphs? But yeah, ideally, at some point we would have a better understanding of which type of information of the graph is actually required for a certain prediction task. And here I should say which information of the input, right? It can be a graph, it can be a simplicial complex, it can be something different, is required to solve a certain task.
One question about the isomorphism test for graphs.
Yeah.
I didn't quite get if you are given two graphs, you color them however you like, and then you run the machine, and if eventually they have if they converge to different colors, then they are not isomorphic. Is that?
And yes and no. I mean, you have to decide from the beginning. You have to decide what the type of scheme is that you assign to both of those graphs. So as I said, you will typically use the degree of the nodes for unlabeled graphs, and for labeled graphs, you take the labels themselves as the initial colors. But if you agree on the same alphabet for the coloring, then indeed you have this isomorphism detection property, or I should say non-isomorphism detection property.
But I was thinking if you just color any alphabet is going to work.
Yeah, as long as it's consistent. So you have to in the chat someone wrote it depends on the hashing scheme. Yes, I mean you have to how can I say that if you start with two graphs and you must only use the information that you can get from a node as such, right? So you need to treat every node that has the same information as kind of equal to all the other nodes. So for instance,
Okay.
if you have if you have a node with degree 3, right, and you have another node with degree 3, then you always have to you have to treat them the same. You have to give them the same color.
Okay, so in a sense, if there is a local isomorphism between two vertices, you are going to label them the same.
I think I would agree with this, but yeah.
Okay. Thank you.
You're welcome, yeah.
So, Bastian, you hinted the possibility that we have a break starting earlier, or maybe resuming earlier. So your second part, maybe it's longer than 45 minutes?
The second part might be a little bit longer. So I would, if it's okay, I would suggest that we take a brief break now.
Okay.
Because then I can set everything up for the bigger journey into topology-based graph.
Okay, then maybe let's stop for 4 minutes and we restart at 5 minutes to 7. Is this?
Very nice. Okay, then let's resume, right?
Yeah.
All right. So, welcome to the second part of the talk. We're now going to discuss how topology plays a role in graph learning, and well, how to leverage topological concepts for graph learning. And this is, I should say, a a collection of our recent research works, and I very much hope that they're relevant and useful. And do feel free to reach out to us, like to my group and me later on, if you have additional questions. Now, we'll be talking about adding topological information to the mix, and we're going to start slow and first add some kind of, let's say, static topological information. But later on, we will also see how to learn topology-based representations, and how to learn, for instance, specific parts of the computational topology process and the computational topology pipeline. So I want to start with a very neat paper, which I think we could have written a little bit differently over the years now, on adding, well, static topological features for graph classification. So this joint work with Christian and Karsten, and the idea of this paper, which we deemed a persistent Weisfeld-Lehmann procedure for graph classification, is that the Weisfeld-Lehmann algorithm that I showed you before can be used to vectorize labeled graphs. By contrast, persistent homology can be used to capture some kind of relevant topological features. And the idea would be that we can combine the two of them to obtain a more general or more generalizable formulation, which is capable of also leveraging higher order information from the graph. So for instance, information about the existence of cycles. And the main thing that makes this fly, the main insight that we had for setting this up, was a distance between the multi-sets of the graphs that we learned. And I'm saying that retrospectively, I would have written this a little bit differently. And indeed, because one of the very nice insights of this paper was also that you can reframe the Weisfeld-Lehmann procedure as a specific thing that operates on certain type of metric spaces. So in a way, we were able to create a framework that is based on multi-set distances and on topological information. And we were able to show that this framework under some conditions yields the original Weisfeld-Lehmann procedure, but it can also yield additional type of procedures. This is why I'm really, really excited about this work, but that's, I think, not quite clear from the title, unfortunately. So we could have done a better job here. Now, as I said, there is a main component that makes this work. It's a distance between label multisets, and this distance is very nicely informed by things like counting distances, by things like a Minkowski distance, because we start with two sets of labels, or I should say two multisets. So we represent them by A and B, and both of them are represented by basically counts over the same label alphabet. So we assume that we have a label alphabet sigma, which has labels L1, L2, and so on and so forth. And then we only need to count how often they occur. We can transform these multisets into count vectors. So instead of writing the label and tracking that, we can just write the counts of each label, right? And remember that, as I said, we assume that we're operating over the same label alphabet, so that always works. And then we can calculate the multiset distance of these count vectors as just some kind of Minkowski distance for a specific choice of P. Typically, I think I might have, I might not mention this specifically later on, but typically P is just set to 1 or to 2. And the interesting thing is, since the nodes and the multisets that they create, of course, they are in one-to-one correspondence based on the WL test. So we now have an actual metric on the graph. And so to give you an example of how this looks like, and you will recall this graph maybe from the previous slide. So if we take a distance between, oh, I'm sorry, there's a label mishap. If we would take a distance between two of these neighboring nodes, we would this should be C and E here, right? So we go from V3 to V5, we take their distance, we take a look at their neighbors. So we say that V3 has 3 blue neighbors and 1 red neighbor, and V5 has 2 blue neighbors and one red neighbor. And so the distance between those multisets is given by this expression here, so by 3, 1, 2, 1. And we can, of course, calculate this easily. Now, this is just an example of how this works in practice, and I'm emphasizing this because it's a really simple way of calculating distances between multisets. There's nothing special or nothing magical about this type of calculation, of course. And we can extend this to a distance between the actual vertices. So that's, I think, crucial insight for leveraging these distances in the WL iteration. So specifically, we can take the WL iteration as it changes the labels, right? We can use the vertex label from the previous WL iteration, as well as the label of the current iteration, and we can build some kind of distance function from that. So the first part of that distance function is a so-called Iverson bracket, so that just basically amounts to 1 if this expression is true, right? And then we have our original multiset distance between the labels in the current steps, and then we have some kind of error term tau, which is a little bit inelegant, but it's unfortunately required to turn this into a proper metric on the graph. And the upside and upshot of this procedure is that based on just the WL iteration, so on this coloring scheme that I showed you, we can now turn any labeled graph into a weighted graph. And if we have a weighted graph, we of course know what to do with that, right? We can calculate its persistent homology. So this gives us this gives us a way to go from a labeled graph to persistent homology calculations. Before we take a look at how that integrates and how it meshes together, let me illustrate this multiset distance, because interestingly, it has some nice multi-scale properties. So since you can think of the WL test as progressively also transporting information from more external parts of the graph to more internal parts of the graph. And this is indeed reflected in the multi-set distance itself. So if you don't do any type of WL transport, you end up with a very, very coarse distance here. If you do a little bit more, you can see that some of the vertices, and by the way, I should say, I'm showing heat maps here, I'm showing the distance matrices essentially. You can show that some of the vertices become a little bit different in terms of the distance. And if you go deeper, you find that there's even more of these different structures. And with 3 steps into the graph, you find that there's even more distinctions between individual vertices. Again, there's an intuition behind that. The intuition is that you collect more information from the graph, which gives you a way to distinguish between graphs and their respective neighborhoods. That's what WL is all about, but that also gives you a way to build some kind of nice multi-scale representations of these distances. And these representations lend themselves very easily to an integration into the persistent homology calculation, into the persistent homology procedure, and specifically without doing anything additional to ordinary persistent homology on a graph, we can already get one procedure that counts the connect components or weighs them accordingly, and we can get one for the cycles. And to exploit this, or to make this work, we actually exploit a very interesting property of persistent homology, namely the so-called pairing lemma. So we know that in dimension 0 and dimension 1, we know that vertices are paired with edges and so on. And this gives us a way to assign to specific labels a specific persistence-based vector. So for the details, I have to send you to the paper. I just want to give you an illustration of how this works in practice. So instead of just counting the occurrence of a label here, so of label 0, label 1, and so on, we now count the persistence of this label. So that's essentially all we're doing. That's how we turn this into a procedure that incorporates persistent homology information. We turn we calculate the persistence over all these individual label instances, and this gives us a way to weight the original WL feature vectors. Now, the bonus, and this is what I mentioned in the beginning, we should have done this a little bit more nicely, and we should have advertised this a little bit more, but we can actually redefine the vertex distance that we defined earlier to obtain the original WL features plus some information about cycles. So by just taking them an ordinary the ordinary binary metric, or the ordinary identity metric that just says, okay, it's 1 if the two nodes are not equal and it's 0 otherwise, through that we can turn the original, we can essentially end up creating the original WL subtree features. Now, I don't want to bore you too much with the classification results, but one very surprising outcome of this technique is that since we can add some cycle information to the mix without learning anything else about the graph, we get a very nice substantial increase in accuracy as compared to the standard WL test. So here we are at 87.26 or something like that. And if we add cycle information, we go up to 90.51. And of course, some standard deviation here. And indeed, this proves to be, given the fact that we don't have to add additional feature information beyond what we already have from the graph, this is a very, very nice procedure that leads to some gains in predictive performance. At the same time, it's also completely static, right? So there's like no proper learning involved here, but rather some kind of clever featureization technique. But it goes to show how relevant this type of technique, this type of incorporation of topological information can be in practice. And indeed, we also looked at overall learnable representations of these type of features, which culminated in a relatively recent ICLR paper on topological graph neural networks, which, despite its name, actually presents a topological layer for graph classification based on some kind of nice, interesting earlier work. This is joint work with Max, Edward, Michael, Eve, and Karsten. So the motivation for this type of layer was really, really simple. And I think I alluded to this, or I hope I alluded to this in the previous lecture. It was motivated by the insight that graphs are fundamentally topological objects, at least for me, but graph neural networks at the same time are also incapable of recognizing certain topological structures. So you might recall one of my last slides from the previous lecture where I said, well, they cannot detect cycles of arbitrary length. When you think about how message passing works, that's actually quite clear, because to detect a cycle, you kind of need to send messages along the cycle, right? So if you have a data set that consists of an extremely large cycle, you also need to do lots of steps of message passing, which in turn means that you also have to add lots of layers and lots of parameters, which makes the training harder. So there's some problems built in to the very fabric of graph neural networks, which makes them a little bit weird for some tasks. So our challenge and our question was what can we actually gain when imbuing graph neural networks with knowledge about the topology of the underlying graph? And that set us up to see what we ended up with. And this is, I'm relying on your previous knowledge from the previous lectures. So we know already that with filtrations on a graph, we can get multi-scale topological features. So the choice of filtration influences the features that we get, but in essence, they are multi-scale with respect to the scales defined by the filtration itself. We also know that we can get the persistence diagrams and many other representations, as I showed in one of the previous lectures, right, to serve as topological descriptors. But we don't yet know how to really obtain good filtrations, how to obtain task-specific filtrations. And we also don't know at least not yet at this point, how to use persistence diagrams. That is how we can use multisets in a differentiable setting. And our work tried to address all of these things at once. Of course, building on the work of others that have come and that have come before us. And to show you what we did, I first need to do a little bit of an interlude and discuss prior work from where I was very happy to have been a co-author. This is work by Chris Hofer and colleagues, entitled Graph Filtration Learning. It's also an ICML 2020 paper, and it had a very, very profound question in there, namely, given a graph, we can do message passing, right? We can also do persistent homology of the resulting representations, but we don't really know how to learn a good filtration for a specific task. So we don't really know how to adjust the function values of the vertices and the edges to make sure that they are in line with what we want to predict. So clearly there's some thinking to be done. And what we ended up doing is we said that, well, persistent homology based on some kind of filtration on the graph gives us a persistence diagram with tuples. We now take this diagram, subject it to a function, to a coordinatization function psi, put that into a neural network, and evaluate the loss based on some kind of task. Now all of this will become clearer in the subsequent slide, but for now we leave the choice of psi open. So we just say this is some way of embedding our persistence diagram into some kind of vector space so that it can be used as an input feature to a neural network. Once we have this, we can, of course, or we could try to train this network, and we could get a loss function. And I mean, this part is clear, I think. So if we have this representation and we put it in neural network and we have a loss, then the gradient, of course, exists from here to here and vice versa, right? The new insight that we showed in this paper, and that is kind of in line with what I showed you in the previous lecture last week, the new insight was that a gradient from here to here, so back to the graph, back to the message passing, also exists under certain conditions, and actually under certain mild conditions. The mild conditions being that we're not allowed to have vertices sharing the same feature value. And that was the insight that enabled us to build a so-called readout function based on persistent homology. So it was just, and I'm saying just in air quotes here, right? It was just something that took a graph and enabled us to build a better representation of the full graph by incorporating some kind of task-specific filtration information. We did this by adding this nice coordinatization function that Chris had developed in previous work. It's a differential coordinatization scheme that is of the form psi going from a diagram, persistence diagram, to the real numbers. And what it does is it projects things down based on the persistence of the point. So it takes a point P and it evaluates that expression here. So 1 divided by 1 plus the one norm of P minus C and so on. The details are not super important. It's just relevant for you to understand that there's two trainable parameters in there. There's a C parameter, a centroid parameter, and a radius parameter. Both of them are trainable, and evaluating one instance of this coordinatization function psi leads to one scalar value. So what you do is instead you represent the full diagram, you represent that by stacking a couple of these representations. That gives you a feature vector in Rn. And you represent, of course, more than one point. You represent it by just summing over individual projections. If you paid attention to what I said about message passing, you might remember that this is very, very interestingly, tantalizingly close, I should say, to things like permutation invariant functions. Indeed, there's some kind of connection to be seen here, because we also need to have something that doesn't depend on the ordering of the points in the diagram, which is one of the reasons why learning with persistence diagrams is such a pesky task in practice, because there's no predefined ordering of these type of points. But anyway, that's our differentiable coordinatization scheme. It works very well. It can be added to this pipeline. It can result in a set of input features for a neural network, and this makes it possible to train a neural network to learn one filtration function that is appropriate for a specific task. So we just have to now think about how to initialize the filtration function, so how to get in a filtration in the first place. And here we, at least for the paper with Chris, we picked a single graph isomorphism network layer, one level of message passing, and then we had a 2-layer MLP afterwards with the sigmoid information. The upshot of this is that our filtration function is a function that goes from the vertices to 0, 1, and then we can of course initialize this somehow, either using uniform weights plus symbolic perturbation or using the vertex degree, but that is a useful filtration function to put on the vertices of the graph and to later on train in a task specific manner. And we can use this in practice, and it works. So it turns out that if this function is injective on the graph vertices, so it has different values on the graph vertices, then the gradient exists, and it affords a very simple integration into existing graph network architectures. And also in comparison to other types of readout functions like a sum or a sum pooling, it kind of worked nicely on some of the data sets, even though of course these gains have to be measured with respect to the overall persistent homology calculations and not necessarily with respect to a graph neural network. So it's kind of hard to benchmark this in practice, but this gave us a very nice idea for subsequent work for building an actual topology-based layer to add to graph neural networks. And this is where we now end our little interlude, and we come back to the first paper that I showed you, so the one with Max, Edward, Michael, Eve, and Karsten. So these topology-based graph neural networks, or topological graph neural networks, are based on similar ideas, but they learn different filtrations at the same time. So instead of just learning one filtration, we learn k different ones. Now, if you're familiar with multi-parameter persistence, and if you've been part of this course, I mean, you've heard a couple of things about those, right? Then don't be confused. So we're not really learning a multi-parameter module here. That would be interesting and very, very hard to do. We're just learning k individual scalar valued filtrations of the graph. And we learn these by starting with the node attributes in the graph. So we have some graph, it has some node attributes x, v, which are living in some d-dimensional space that will be helpful for the subsequent part of the diagram. We apply what we call a node map phi, which is just a function from Rd to Rk. And Rk we treat as a component-wise way to have different filtrations in the graph. So you can see that we disentangle that. We are now in Rk, and we evaluate these k different filtrations on the graph. We get k different persistence diagrams, or actually a little bit more, right? Because you could also create persistence diagrams that contain cycle information and so on. But let's just say we have k different persistence diagrams. We then apply our previously shown coordinatization function to every one of them, which leads to a set of vectors that we get. And then we aggregate them with the existing vectors, with the existing node features, to obtain a new node representation in the end. And the main thing to understand and to remember here is that this leads to a new node attribute, x tilde, that is also d-dimensional. So this seems a little bit weird, right? So we start with something in Rd and we end up with something in Rd. Yes, it might sound weird, but the interesting thing is that this whole pipeline in between, these whole aggregation steps and views and persistence diagrams and so on, they give us a way to inform the persistent homology calculation by the node features. and vice versa to inform the node features about topological structures. And this is where the power of this new paradigm, of this new model comes into play. So in a way, the new node attributes of the graphs are informed by topological structures that can be detected using persistence diagrams, using the learnable filtrations. So I do want to emphasize that there's two relevant learnable steps in there. There's this step psi, which projects the diagrams, and there's this step phi, which learns the individual filtrations. Both of them are learnable. Both of them are end-to-end trainable and thus task-specific. And this is what makes the architecture fly in practice. So as I said, we now have to think about how to choose phi and psi. Now, this node map function, so the map that gives us a set of filtrations, this can be realized using some kind of neural network. So in our case, we picked something like an MLP even, right? The coordinatization function, interestingly, psi, can be realized with the differential coordinatization function that I showed you before, so with the work by Chris Hofer and colleagues. But it can also be realized using any type of vectorization or other type of featureization function that involves persistence diagrams. So it could be realized with persistence landscapes, with persistence images, or with some of the other descriptors that I showed you in the previous course last week. And this gives you a really nice recipe, of course, to set up a topology-based graph layer now, because it literally permits you to slot this layer in, and the graph neural network can just continue message passing as if nothing has happened, right? Because the layer acts as, from the point of view of a graph neural network, it acts as a neutral buffer. It takes d-dimensional vectors as inputs, and it takes d-dimensional vectors as outputs. So from the point of view of the network, of a neural network, nothing else happened in between, which is good because it means that you can continue doing the message passing at lower levels if you want to. And the relevant theoretical insight for us was that this layer, which we call toggle for topological graph layer, is actually more expressive than the one-dimensional WL test, by which I mean that if the WL1 label sequences for two graphs diverge, there exists an injective filtration function that we can hopefully learn, such that the corresponding persistence diagrams are not equal. But secondly, there are also graphs that WL1 cannot distinguish, but toggle can distinguish them. So two example graphs that we can distinguish based on persistent homology quite easily are these two guys here. So this is a graph with two connect components. This is a graph with a single connect component. But likewise, it can also be characterized and distinguished by noting that one has two cycles and the other one has only a single cycle, right? But the main insight is that indeed this new layer, which is why we were excited about it, gives us a way to scale up the expressivity of persistent homology and take it to a regime that cannot be reached by WL1 alone. And so naturally, we were of course curious to see how this performs in practice and what type of gains we can expect from this method. And now I want to have a little bit of a meta discussion here, because I'm not saying that our experimental setup is the best setup that could have been done for any such project, but I do want to stress that we thought a lot about this and we tried to make this into a useful setup. We accomplished this by taking an existing GNN architecture, replacing one of its layers, one of its message passing layers, by our layer, by toggle, and then measure the predictive performance. Now, this sounds a little bit weird at first, but the reason behind this was that we wanted to ensure in this strategy that the number of parameters remains approximately the same. So we wanted to ensure that we have a fair comparison of these different neural networks, because what you will often see in some venues and in many machine learning papers is that people are presenting a new layer or a new type of strategy, and then they add this in addition to something that already exists in a neural network. And thus, of course, increasing the parameter budget of the neural network, which, well, on the one hand, it makes it harder to train potentially if you don't have enough data, but on the other hand, it also gives the network more opportunities to learn some kind of other functions. And what you really want to see is, given the same number of parameters or almost the same number of parameters, right? Do you get an insight from one formulation as compared to the other formulation? And this is what we set out to do. So our goal was not to say, haha, with this architecture we can beat everything, but our goal was really just to say, okay, if we replace this layer here, this is how your expressivity changes, this is how your predictive performance changes. And to test this, we of course started out with some synthetic data sets, because it's really, really important in the beginning stages of any project to understand that what your method could be doing if everything was nice and if the universe was a perfectly nice and just place. And to simulate this, we used two types of synthetic data sets that had a binary classification problem. The first data set is called the cycles data set. The second data set is called the necklaces data set. The cycles data set is characterized by either consisting of a single cycle that is relatively long, or a set of smaller cycles, which are typically triangular but don't have to be triangular in practice. The necklaces dataset, on the other hand, consists of a very linear structure with some cycle around here, or the same structure, but the cycles are being pushed to different ends. So it's like the connectivity of the cycles is essentially being changed. And the relevance of these data sets can be assessed by thinking about the fact that these simple topological structures are nevertheless challenging to detect with standard graph neural network architectures. So despite this being a relatively simple task, or like for human beings, it would be very, very simple to classify the cycles data set, right? Because you literally just have to count the cycles. But nevertheless, it's not necessarily trivial to accomplish this with standard graph neural networks. And we can see why that is the case. So for instance, if we take our WL subtree features and we count, for instance, the number of degrees in the graph, you will see that this indeed does not lead to anything, right? So regardless of how deep we go into the graph, so I said that the colors stabilize, right? The colors stabilize up to renaming, and you can see that here there's only a single color being generated regardless of how deep we go into the graph. So we have to conclude that these cycle graphs cannot be distinguished just based on their WL1 information. So this is nice, but of course it's also constructed that way, right? I mean, we set it up so that it would work. With the with this being done, we can kind of take a look at the empirical expressivity of our method on this type of data set. And yes, I realized that that this data set is easy to classify for persistent homology, but as you can see, it's very hard to classify for your regular GCN, at least unless you change the number of layers. So there's three relevant curves to consider here. One is the ordinary WL test. The other one is a GCN with K layers, and the blue one is the same GCN with K minus 1 layers, I should write technically, and one toggle layer that we added, I think, at around the second or third position or whatever, whenever it's appropriate, of course, right? So it's either the first layer, the second layer, or it remains the third layer regardless of how many layers you have. And one thing you can see is that to get a good classification performance, you don't need lots of layers, at least for this data set you don't, right? So the GCN with one toggle layer is almost always at at more or less 100%, right? Plus or minus some minor standard deviations. Whereas with the GCN, you need up to 3 layers to match that performance. And this is clear because the cycles that we split our big cycle into have a certain maximum diameter, right? So you need to detect this diameter first with a couple of layers before being able to make a classification of the individual graph. By contrast, the ordinary WL test doesn't work here, and this is okay as it was constructed that way, right? Now, moving on to the necklaces dataset, here things are a little bit different. So here we have the WL subtree features, and they do change a little bit. So for some of the datasets, we do get different histograms, but not in all the classes. So for instance, for those two guys here, you will find that it's virtually the same histogram, but there are classes in there where the WL is okay in distinguishing between the graphs, but in general, the separation between this and the WL test is not great, is not good in practice, which is also what made it a good and useful data set. Again, let's take a look how that works in practice. And here we find a very interesting phenomenon, which one might almost call undersaturation, if one was so inclined, because we see that our method, the blue one again, right? So GCN with one toggle, with one topology-based graph layer, it always works out, right? You get some standard deviation, of course, but it's pretty much perfectly capable of distinguishing between those types of graphs. The GCN is really not doing a good job here. So its performance increases as you add more layers, but it also increases very slowly in contrast to to toggle, right? So it really needs a lot of information and a lot of graphs to actually learn and approximate our performance in practice. Second, of course, you see that with WL, the kind of a similar pattern emerges. So you have to go very deep into the graph and have to do a lot of WL iterations in order to approximate the performance of the topology-based graph layer. Now, so far so good, but how does it work in practice? How does it work with more benchmark datasets, right? And I do want to stress here, before we go into that table, I do want to stress that every benchmark dataset was, well, maybe almost everyone was once pitched in order to make a certain method look good. So this is kind of maybe relevant to take into account, because over time many things can become benchmark datasets, but it's not clear whether they should have been, or whether they were just being pitched to pitch a specific method itself. But anyway, one thing that we did first, and I have to stress this when you look at this table, and you might see some accuracies that are weird, we picked datasets for which it was suspected that they leak information into the node attributes, so that their node attributes actually contains information that is very relevant and conducive for their classification. We picked those, and we knew that when we picked them, that the utility of topology-based features would be decreased, because if your node feature has a dimension that says here's a cycle, then of course you don't need an algorithm to detect the cycle, because the node feature already encodes the presence of the cycle. That's of course a hyperbolic claim. I'm just saying this here for the sake of an intuitive understanding of the shape of the problem. To counteract this, so to put all the methods on equal footing, we replaced all the node features by random features, and we checked the performance of the resulting representation. And one thing that really sticks out here is that if we start with one method like a GCN with 4 layers, and we replace one of these layers by a topology-based graph layer, we really find that this increases predictive performance quite considerably. So the presence of topological information is really apparent here, and the utility of this information is really apparent here. This even holds for other architectures. Sometimes the gains are even bigger, so the GAT, the graph attention network, for instance, really goes up more than 10 percentage points on average when being trained with random node features here. And in general, this works really nicely. We even have some node classification data sets here, but we're not going to talk about them. Of course, this task is a little bit artificial, I concede that, because we took away information that the graph typically has and we replaced it by random information. So of course, if it's about just beating the state of the art, then things look a little bit different. So let's take a look at what happens when we do that. Here the situation is still good, but different. What I mean by this is that we can still see that compared to our baseline, so baseline, I mean the original graph neural network that we did not modify. So compared to this baseline classification performance, we almost always improve, except for the enzymes data set, which is weird in many ways. It's also a very small data set, so it has about, I think, 600 graphs. And the proteins full data set, where the gains are minor or very well within a standard deviation, right? But for most of these data sets, we improve upon the baseline. So for instance, sometimes by 7 percentage points, sometimes by even more, although again, that's enzymes, so it cuts both ways, right? It's a we shouldn't really think about it too much. Maybe by 5 percentage points, whatever, by 8 percentage points, right? So there's always the topology-based information is not very detrimental, apart from some minor mishaps with maybe the standard deviations. And in the best case, it's actually useful to help a graph neural network learn something. At the same time, and this is the bad message or the negative message of this plot, is that the best performance that we observe overall is not driven by the availability of topological structures. So there's a method called gated GCN, and this one outperforms a couple of methods on these data sets. Or there's a WL algorithm based on optimal assignment strategies, which also outperforms a lot of things here on the DD data set. So in a way, this is like a mixed bag of results. So it works if your node features are irrelevant and don't contain any type of topological information, then adding topology-based information is useful. But in general, for these node and graph classification benchmark data sets, the availability of topology is maybe not the crucial factor. And this is maybe unfortunate, because that also means that maybe we're missing out on new data sets and on new methods. But I'll talk about this at the end. So as we slowly approach the end of this lecture, I also want to show and highlight a very different approach that doesn't make use of methods from computational topology as such, but that makes use of paradigms and ideas from computational topology and still use them gainfully in graph representation learning. So this is joint work with Leslie and Karsten, and it's entitled Filtration Curves for Graph Representation. It appeared in the KDD proceedings in 2021. And the motivation for this is the observation that if we have a filtration for graphs, we can relatively easily obtain a persistence diagram, and we can represent those diagrams very nicely by Betty curves. And I already showed you in the lecture last week that one can have lots of fun with Betty curves. One can use them as piecewise linear functions and calculate means and so on and so forth. But the other question for us was, what if we use a more general descriptor function here? So what if we don't just do the filtration and calculate persistent homology, but what if we actually evaluate some kind of other function alongside the filtration. And this led to the concept of what we call filtration curves. And as an example, and you can see that this is the same graph that cropped up a couple of times now in this lecture. As an example, we could take, for instance, the node label histogram as a descriptor function. So we just take a function that counts how often a certain node label occurs. That's a valid function, and it's easy to assess. So suppose we do this by having the following filtration. So that's our first filtration step. We have two blue nodes, one red node. That's the second filtration step. We now have 3 blue nodes and still 1 red node. That's the third filtration step. We now have 4 blue nodes. And the fourth step tells us, finally adds the second red node. And we can now disentangle the image of this node label histogram function by getting these nice curves here. So as you can see, this is a filtration step 1, 2, 3, 4. The red node count doesn't change until the very end, so it stays at 1 until it goes up to 2, and the others change in every step. So this is a very simple way of evaluating a function alongside the graph. The big question is, of course, why would you do that, or what can you do with this paradigm? What does this help you in practice? Well, the interesting thing is that you can take those individual filtration curves, disentangle them based on the label, for instance, and since they are based on Betti curves in a way, they also inherit a lot of their properties. So you can do the same thing. You can do mean filtration curves. You can use them for hypothesis testing, and many other approaches. But it all boils down, this calculation all boils down to the choice that you use for the descriptor function. So what is a good way to filtrate the graph if you do this? And what is a good descriptor function later on to have as a nice descriptor of your graph? So for the filtration functions, we looked at a couple of things. We looked at native edge weights of a graph. This is, of course, if you have those graphs, that's great. We looked at the degree function, which is, I would say, the canonical choice of filtration function for unlabeled graphs. We also looked at the Olivier-Ricci curvature, which is very nice and very easy to calculate, more or less, unless your graph gets too big. As a side note, I do want to stress that Olivier-Ricci curvature is a really exciting concept that I think has a bright future in graph learning. And last but certainly not least, you could also use concepts like a heat kernel signature, so something that is based on a graph Laplacian, and see how that fits into there. And again, as I said, the descriptor functions, so the things that you evaluate alongside the graph, they can be anything that you want. Two choices stick out for us. The one is the node label histogram, if you have node labels. The other one is just something like a number of connected components, which is in a way, right, related to topology, but it's not exactly the same. It's more like a very generalized Betti curve. The important thing I want to stress here is that all the filtration functions that we picked here, they are shallow for now. So we are not yet learning a task-specific filtration. We could do this, but we're not doing it yet. And I do want to point out that this very simple technique, so you put this through the you evaluate a filtration, you evaluate a function alongside that filtration, you then use the image of that function to represent your graph. This very simple technique is relatively competitive when you compare it to more complex techniques and to more complex, heavily parameterized methods. So you can see this with some of the graphs that have native edge weights. We outperform other approaches for them. So for DHFR MD, for instance, or ERMD, right? But even for non-negative edge weights, we're doing surprisingly well. We're not the best performing method, but we are consistently performing on a good level. To show this, let me show you a very nice plot that Leslie came up with. So this is showing you the absolute distance to the accuracy of the best method. So essentially what you want to have is you want to have a very, very small standard deviation here. So very, very small whiskers of the box plot. And ideally you want to be at 0 because that would mean that you always win. And interestingly, our filtration curves framework, which we abbreviated FC here, is consistently doing very well. It's not the best method, right? So it has a non-zero standard deviation, of course, but it's consistently performing overall. Whereas other methods have a much, much larger spread. So they are very good in some tasks, but very bad at others. Again, we don't have a nice theoretical explanation for this yet, but this might hint at some kind of, dare I say it, almost universality of topological information, because you might not be always able to use it gainfully, but it at least gives you a literal competitive edge in comparison to other methods. And this now brings me to the conclusion that I want to use to start hopefully a discussion. So I think we've seen that hybrid models, which are always likened to something like a chimera here. So hybrid models, by hybrid models, I mean models that don't necessarily just follow one paradigm, but that try to integrate multiple paradigms. For instance, the paradigm of topology that increases expressivity, and the paradigm of message passing, which is conceptually very elegant. So these type of hybrid models, I think that I've demonstrated that they show particular promise for graph classification, because they can literally leverage the best of both worlds in an ideal case. Nevertheless, there is a dark side to all of the things that I showed you, and that is, if all you have is nails, everything looks like a hammer. That's how Mikael Vejdemo Johansson put it. So I know that it's not the way that you would usually put this, but the results that we observed in Toggle in our topology-based graph layer experiments, they were a little bit disconcerting, because they showed that a lot of the data sets actually contain lots of information, lots of structural information about the graph. And this might come back and bite us and actually turn out to stymie progress in graph neural network research, because the classification of such graphs, or any type of learning process, as it were, on these graphs, is not necessarily requiring any type of structural information. And I think that's a problem, because if we're collecting the wrong data, and if we're measuring the wrong things on this data, then we also develop the wrong methods. So we develop methods that are, from the outside, we might think, and we might fool ourselves into believing that. We might fool ourselves into believing that, oh, well, they are extracting some structural information. But in the end, they're just very, very good at leveraging structural information that is already there, that has been put into the data set by some modeling decision. Kind of like we modeled the co-occurrence network, and the modeling decision influences the things that you can see in the data. So again, this is a little bit of an open conjecture, but it's a point that is dear to my heart that I want to impress on people. Think about the data set, think about how it has been collected before you just use it in your benchmarks, because this can make a difference between a good method and an actual great method. Nevertheless, I don't want to end on a pessimistic note. I believe that higher order structures, and this could be cliques, but this could also be higher order simplices, or even cycles, or something like this, they can be crucial in discerning between different graphs or even data sets. So there's great work by Buritzas and others on leveraging cliques, for instance, and imbuing graph neural networks with additional information about these sort of things. And I think this just points to general utility of these structures. At the same time, linking it back to the previous thought, we're still very much at the the beginning when it comes to that, and we need to understand our own data a little bit better, and we need to understand the concepts and the models and their overall empirical and theoretical expressivity. We also need to understand that a little bit better. That brings me to the end. Just for the sake of completeness, and if you're watching this on the recording, I do want to add this information again, so feel free to contact me. Check out our group's website on idos.group, or my own private website for some for a list of papers and for more resources on computation topology. And if you want to give me anonymous feedback, I would also be happy about this, but of course also feel free to give me non-anonymous feedback. I'm trying this out for consistency reasons. So thank you very much to the organizers for having me and for enabling this great workshop. Thank you so much.
Immediate feedback is that this was wonderful. I mean, absolutely amazing. Amazing level, amazing quality of presentation. Thank you very much.
Thank you very much. That's really kind. I leave the anonymous feedback always open, because sometimes for students, if they want to criticize something, they might not be very willing to say it to the professor's face, right? Even though I wouldn't mind, but I know that this is hard to do in practice, right? So, but yeah, thank you very much. That's very kind. Oh, I think we have lots. Oh my goodness, I see the chat explode. Let me open the chat. I'm sorry.
There's a question which was asked early, a long question which was asked by 7:30. Can you read it?
Yes, I see it. So the architecture for the DNN is encoder-decoder, where the topological information is used for optimizing the loss. Does the WL hashing necessarily has to code topological information? I'm thinking about adding information to the hashing apart from only topological information. That's a very insightful and deep question. I'm not sure I can answer it very well, but I would say the hashing doesn't necessarily have to encode this topological information. So it only has to ensure that neighborhoods with similar counts are mapped to the same hash. So it has to be a perfect hashing scheme, but that's all. So it doesn't have to be aware of topology, and maybe it will be a very exciting step, actually, a very exciting direction to try to have topology aware hashing functions for these type of graphs. That would be, I think it would be really interesting, but I can't comment on this anymore. I'm sorry.
A minor question. You mentioned curvature as a filtration function. Is this something which is defined at every vertex?
It works. For some graphs, it works relatively well. I can briefly try to go back, but I unfortunately don't recall. I don't recall whether we used it for the graphs on the current slide. But I mean, Olivier-Ricci curvature is very powerful in distinguishing between different graphs. And it can even help distinguish some graphs, like strongly irregular graphs, that you cannot easily distinguish with WL tests again. But yeah, I would say that it's a very exciting concept to try out. I have to admit, I'm a curvature fan, because it combines kind of geometrical and topological aspects. So it always has a very very big place in my heart. But yeah, I don't know how well it actually fits into this overall framework beyond that. I'm sorry, that was it was not a precise answer.
Is it easy to compute and fast to compute?
Relatively. So you have to, at least for Olivier-Ricci, you have to solve an optimal transport problem. But if your graph is not too big, then you can do this relatively quickly. There are some tricks around that and some speed up techniques. But yeah, there's also other combinatorial variants of curvature which have proven their relevance in graph learning. And these are relatively quick to calculate.
Bastian, one of the attendants, Bertrand Miquel, asks for any summer school or congress related with the topics that you explained, or in general about topological deep learning applications.
Yeah, I mean, unfortunately, there's not a dedicated summer school yet. There is, I think, the LogML summer school in London, which has a lot of geometry and topology in it. It's not specifically geared toward topological machine learning or topological deep learning, as it were, but it certainly has, it touches those bounds. There's also the Applied Algebraic Topology Research Network, or AATRN for short. You can find more information about this on my website. It's not created by me, but I have the pleasure and honor to be one of the co-directors there. We offer lecture series every week for free, but the lecture series are not ordered in any way, shape, or form with respect to topological deep learning. So there's always a mix of problems in applied topology, problems in let's say metric topology maybe, and then every once in a while we also have a research talk about machine learning in general. But that those are kind of the main foci that I can think about. There will hopefully also be in the future a new set of or series of workshops at machine learning conferences, but so far I have to say this with some shame on the record. So far, we haven't been very lucky in applying for additional workshops. So this used to be a little bit different. During the pandemic, we had a very nice workshop series called Geometrical and Topological Representation Learning, GTRL for short. We're trying to get this back on track, but the conference organizers have to be nicer to us here. There's also TAGML, TAGML, which is short for topology, algebra, and geometry. This is also an initiative that I have the pleasure to support. They are also trying to set up conferences and workshops, but we had some very bad luck, unfortunately, the last couple of weeks with applications for this. But yeah, those are kind of the focal points. But I hope that it will become more and more over the next few years.
Thanks a talking for providing a wiki address for workshops and conferences in the chat. That will be useful.
Very nice. Yeah.
And
I hope there will be more of those. There will also be a conference on applied topology next year in Chicago, which will cover, I hope, some of these aspects. But it's more broad than topological machine learning and topological deep learning.
Yeah. This may be one last question. Are the computations implemented in C++ or Python?
Both, but I think nowadays most of the work that we are doing is Python, but it often calls behind the scenes, it calls some older C++ code. There's Ulrich Bauer from TU Munich is very, very active and very, very good at writing efficient C++ code for calculating topological features. So this is it's really great to build on his work.
Well, so unfortunately we have reached an end, not only of your lecture, but of the course. It was a long series of lectures. Maybe Aniceto wants to summarize the outcome, if you may.
Well, I believe, well, first of all, wow, what a brilliant ending, Bastian. That was great. That was great. It was a pleasure. I mean, the 2 hours just flew away. Well, I believe it's for summarizing the success of the course, it's a task for the participant here, and I believe I talk through Carles and Federico as well. We would like to express our deepest gratitude, first and foremost, to the lecturers for the wonderful job they've done, in which they have excelled in both scientific quality and generosity. Moreover, and I can attest to this, they have ignited the spark in many of the participants to develop new ideas and even long-range project concerning different aspects on TDA. So again, and in order of appearance, Anna, Vidi, Robert, Aina, Ruben, Bastian, thank you very much. And also, Carles, Federica, and I would also want to warmly thank the entire audience for your participation, without which this course would have not been possible at all. Very especially to those of you that have engaged in the very good questions, comments, remark here in the chat or by mail, that I know that Federico has sent many mails concerning the course. And this has allowed us also to get a very good feedback on the progress of the course. So, well, with the hope to meet you, some of you, many of you, preferably this time in person, if possible, we just send you a very warm greeting, and I guess that'll be it, right? Well, what do you think, Federico?
Yes, indeed. Yeah, I cannot say it better than what you have said. Many thanks to everybody, and hopefully see everybody in the next course organized by the Red.
Yes. Let's see. Let's get into it.
Some participants are already asking for a continuation. Eh?
Indeed. Oh, of course, and with this way to say thank you, I also answer all the people that in the chat are thanking, especially the lecturers, for their wonderful job. So thank you.
Thank you so much. Also, like, I mean, I think I might be the only lecturer at this point here, but on behalf of the others, I can also say really thank you very much for having all of us. I mean, it's I know from doing this myself that I mean, I haven't organized something of this scope before, right? So I know that it's a lot of work, but it's also really really appreciated, I think, by everyone, in particular by students that are just starting out and that are learning about new topics here. And I know it's a lot of work, but I should say I very much appreciate the effort. It's really great that this is being done, and I hope to also see many of you in either virtually or in even in real life at some point, right? So so thank you very much for doing this. This is really great.
Thank you. So I guess that's all, folks. So
that's all. See you next time.
Before we leave, are you sending an email to the participants for if a second part comes up?
I beg you. It's somebody talking here. I can. What?
Yeah. Are you sending an email to the participants in case a second part comes up?
Oh yeah, absolutely. We have the list. So we'll be bothering you again if something like that is coming up again.
Oh, great. Thank you. And thank you very much to everyone.
Thank you.
Bye-bye.
Bye then.
Thank you very much. Amazing.
Thank you very much. Bye. Thank you.
Bye.
Bye. Thank you.